Okay, welcome. So today I'd like to talk about potentials, electric potential energy, and I'd like to start with what it means to go from a higher potential to a lower potential, or a higher potential energy to a lower potential energy, and to differentiate between the two. And then I want to talk about how we calculate electric potentials from different charge distributions, in particular from in a constant field from a sheet of charge, and then specifically from just an arbitrary charge distribution. So that's what we're going to do today: calculate potentials, potential energies, talk about the difference between potential and electric potential energy. Sorry, I keep saying it. Between electric potential and electric potential energy when we talk about going from higher potential to lower potential, and calculating potentials and potential energies from different charge distributions. Okay, so as a reminder, electric potential, V, is defined as electric potential energy per unit charge. It's got units of joules per coulomb, which is also a volt. And let's just start with an example. Let's say, for example, I have an electric potential which is 300 times X. And so unit-wise, times X, where X is the distance along the X-axis. So your potential increases as I go along the X-axis. So let's make that joules per coulomb meter, so that if X is in meters, then V is joules per coulomb. It's the units that it should be. So this is an arbitrary potential function that I've given you. It does increase just in the plus x direction, and then that means it would be constant along the y direction, right? It would be constant along a line in that direction. All we've seen so far are potentials due to point charges. As an aside, remember that the potential due to a point charge was kq over r. That's not something that increases with x. It actually decreases with distance away. And so it's created by a different charge distribution, right? This is for a point charge. The charge distribution that creates the potential V equals plus 300x is an arbitrary charge distribution I haven't told you about yet, but it actually turns out it's what you get in a constant electric field. We'll see why that is later. For now, I'm just giving you this arbitrary function. Now, think about what happens. If I take, so the potential, let's just take the y-axis, and so that's where, x equals 0, right? The potential, in what direction does the potential increase? The potential is 0, V equals 0 at x equals 0, right? And at x equals, let's say, 10 centimeters, right? Then V is equal to 300 times 0.1 is 30 joules per coulomb, right? The potential increases in the plus x direction. That actually should be pretty clear from the function V equals 3 plus 300x. The potential increases. So what does that mean for the potential energy if I put a charge in this potential? So let's take a point charge, a test charge, a proton or an electron, which are opposite charges, and they're going to have different kinds of motion. But let's just take a test charge, Q, and I'm going to make it a green test charge. And let's just put that green test charge at some point. Oh my gosh, sorry, I'm having a little trouble with the iPad. Okay, so there's Q, and if it's a positive charge, regardless of the charge, if I move to the right, V increases, right? V increases to the right, V decreases to the left. But what about the potential energy? The potential energy, if Q is a positive charge, since the potential energy, U, is equal to Q times V, then if Q is a positive charge, right? And that's just if Q is greater than 0, if Q is a positive charge, therefore U also increases to the right, right? Because U is equal to 300 x times Q, and let's just say that Q is a proton. No, let's not even do that. Sorry. Just for the heck of it, let's say Q equals plus 1 millicoulomb. So it's a charged object with a charge of plus 1 millicoulomb. So, whoops, let me go on to the next page. So, U equals QV equals plus 1 millicoulomb times V, which was 300x joules per coulomb meter. So therefore, U is equal to 0.3x joules per meter, where again, x is just the distance along the plus x axis. So U increases as I move to the right along the plus x axis. So, but not as I move. I'm sorry, now we got to be careful. We are in a potential. We're in a potential in space of that increases from x equals 0 as 300x. That was just an arbitrary thing that I gave you. And so the potential increases to the right, and the potential increases to the right. So if I take a test charge plus Q, which I just made a 1 millicoulomb, my green test charge, as I move that to the right, its potential energy increases. So its potential energy increases, right? The potential increases, the potential energy increases. So what happens if I let go of the Q, of the charge Q, and just let it move on its own, right? Naturally, it wants to go to where its energy is lower. So the charge plus Q is going to move naturally to the left, right? It'll go in that direction if I let go, because it wants to go to where its energy is lower. It's going to go to where U is lower and kinetic energy is higher. It's going to naturally move to the left. But what if I take instead a minus Q? What if I took a charge minus Q, a point charge minus Q, and now what is the potential energy of that point charge? Again, remember, we're just in a region of space. We're in a region of space where, again, I'll circle this, where the potential increases 300x. It has nothing to do with these test charges. We're in a region of space where the potential goes to 300x. So the test charge minus Q, it's got a potential energy for that minus Q, potential energy, U is equal to QV, which is, in this case, minus Q, right, Q is the arbitrary charge. Maybe I guess I could have given these subscripts. Let me just do it this way. Minus QV, because that's what it is, rather than making two different variables. And so we've got minus 1 millicoulomb times plus 300x joules per coulomb meter. And so we've got the potential energy is minus 0.3x. So what direction does the potential energy of minus Q increase, right? As we move the minus Q to the left, the potential energy is going to increase, because U goes as minus 0.3x. So as I go to the left, the potential, as x gets more negative, U gets larger. I didn't actually write that word here. Increases. That's what the arrow was meant to mean. Increases. Right? But for the minus Q in a potential that increases to the right, if you put a minus Q in it, the potential energy increases to the left. What's an easier way to see that? Easier way to see that is just to say, hey, let's put the minus Q. Never mind what I was about to say. Okay, so the potential energy increases to the left is all I can say about that. So for a positive charge, the potential energy increases in the same direction as the potential increases. For a negative charge, the potential energy increases in the opposite direction that the potential increases. So think about what the potential, what these directions must have to do with, right? We're talking about how something, again, these aren't vectors. This is just how does it change, right? Does it increase or does it decrease? And think about when you put a positive charge in an electric field, what direction is the positive charge going to move naturally? The positive charge naturally moves along electric field lines, right? That's what an electric field is. It's showing the direction that a positive charge will move. The electric field line, by definition, is the direction of the electric field line is the direction that a positive charge will move. Okay, seeing that a little clearer, the electric field is the direction that a positive test charge will be pushed, right? That's the electric field line. It's the direction it's going to push a positive test charge. So, what does this say? This says that the potential V must decrease along electric field lines, right? So let's take, for example, let me just draw you a new picture. Let's just take a positive charge. Let's say we've got a plus Q. Oh my gosh, sorry. I've had problems. And let's say that the plus Q, if I just let it go, then the plus Q were to... sorry. Okay. And the plus Q were to move to the left. Then there must be an electric field pushing it to the left. There must be. If if it naturally moves to the left, there must be an electric field pushing it to the left. And that is the direction in which the potential decreases. It's the direction in which the potential decreases. So the potential decreases along electric field lines. Now, so what happens to the potential energy? It also decreases along electric field line. Right, because the plus Q wants to move in the direction of electric field lines. So that's the direction it naturally wants to go, and so that's the direction that the energy of the plus Q naturally decreases. Okay, I want to again be clear here that I am showing a charge plus Q moving in an electric field E. The electric field E is not the field of the charge. The charge plus Q is moving in an electric field E. Okay, there, I've written that down. So Q is moving in an electric field E. And the direction, and so it's going to move to where its potential energy decreases, and that must be the direction in which the potential decreases. Now remember, the potential has nothing to do with the charge plus Q. It only has to do with the field. And so the potential decreases along E. But what happens if I have a negative charge Q? So now let's take a negative charge Q and put it in the same field. We're going to just repeat what we said on the previous page. The negative charge Q is going to naturally want to move against the field lines because field lines are the directions positive charges are pushed. Therefore, negative charges are pushed the other way. So that is the direction of decreasing potential energy for the negative charge Q. So U of minus Q decreases in the opposite direction of the electric field. So you just need to understand that. I think that if you understand the first part, that the potential decreases along E, and therefore the potential energy of a positive charge decreases along E, then you can think through and say, okay, what if it's a negative charge? If it's a negative charge, it's going to move in the opposite direction. So negative charges, energy, are going to decrease when you move opposite E. But in that case, remember, and this is where you tend to have a tendency to forget, the potential was decreasing, and the potential is still decreasing along E, while the potential energy is increasing in the other, okay. Okay, so I've said that twice in two different ways. But what's one of the things that we're interested in is the fact that potentials and potential energies increase or decrease along field lines, because that's the direction that a charge would be pushed along a field line. So that's going to increase or decrease the energy of a particle. Okay, but what does that mean then for where the potential is constant? Where does the energy not change? So here I've got a point charge and the electric field of that point charge. And so we know that, so now this is a point charge that itself is creating an electric field. And I'm interested in the potential due to the point charge, right? The potential due to the point charge. Whoops, let me change the color. The potential of point charge Q decreases along field lines because that's the direction that if I put a positive charge in that potential, the positive charge would go along the field line to a lower potential energy. Okay, so where is the potential constant in this diagram, right? So and I don't mean zero, I mean constant. If the potential right here at this point is 3 volts, 3 joules per coulomb, where else is it 3 joules per coulomb? Well, it's 3 joules per coulomb here, 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 and here. It's 3 joules per coulomb at the same distance away from Q everywhere. So if I connect a line between those points, right, this is what's called an equipotential surface. The equipotential surface for a point charge is a spherical shell, right? Because this is actually 3 dimensions, a spherical shell. Anywhere over that shell, the potential doesn't change. The potential only changes if we follow a field line. So perpendicular to field lines, that was the punchline here, perpendicular to field lines. The equipotential surface, the surface over which the potential doesn't change, oops, this says charge, is perpendicular to field lines because potentials only change when you move along field lines. So what does that mean? What that means is if I take another charge, a test charge, let's put a test charge at this point, test charge Q in the vicinity of our other charge Q. It doesn't matter if they're the same charge or a different charge. We can just call this Q1 in order to differentiate them. If I move Q1, let's say closer to Q, if I move it closer to Q, it takes me work to do that because I'm moving against the electric field. If I move Q1 farther away from Q, actually it'll naturally do that, right? Because its potential energy will be going down, and so it will gain kinetic energy if I just let it go. But if I move Q1 anywhere along the sphere, the spherical shell at the radius r, it doesn't take any work to move it because I am moving it perpendicular to the field. And so it takes no work. There is no change in energy along an equipotential surface. So let me go back to the example I started with a potential that changed linearly with x rather than this one that changes with 1 over radius, right? In this case, v equals v of the black charge q, v equals kq over r, and so therefore u of the red charge q right, so the potential of the potential energy of the red charge Q only changes if you change the radius. The potential of the red charge Q only changes the potential energy of the red charge Q only changes if you change radius. Okay, let me go back to the slightly easier to deal with constant field. It is actually a constant field, but we haven't really shown that yet. And let's just say again the potential goes as plus 300 x. Units are joules per coulomb meter. I had drawn a line perpendicular, right? And so here's the thing. If I take a test charge Q in that potential, a test charge Q, that charge is naturally going to want to be pushed this way. Naturally, it's going to go that way. If I push it that way, I've got to do work because I'm moving it to higher potential energy, right? So I got to do work. It's going to change its potential energy in that direction. It's going to change its potential energy in that direction. But if I move the charge along this red dotted line, there is no change in potential energy. Okay, so here I've shown, test charge Q in a potential 300x. If I move to a higher x, I'm increasing its potential energy. That's to the right. If I move to a lower x to the left, I'm decreasing the potential energy. But if I move up or down, if I move along the y-axis, then I'm not changing its potential energy at all. This is an equipotential surface, and equipotential. Whoa. Okay, so in 3 dimensions, this would be a plane that the plane that cuts the x-axis. Okay. So let's just talk about. We'll talk more about equipotential surface in a little bit. Let's just talk about how we might. I've already hinted at how we might create a potential that is constant with distance instead of 1 over r for a point charge. Okay, as a reminder, we calculate our delta u's as minus w, and w is f dot ds, so therefore delta u is minus f dot ds. And let's see how that works for a different configuration than a point charge. Let's say that we have a plane of charge, or a sheet, back to the sheep, a sheet of charge, or a sheet cake. So try and draw it in 3 dimensions. We've got a sheet of positive charge. It's perpendicular to the x-axis, so the x-axis is perpendicular to the sheet. So the electric field excuse me, to the right of the sheet points in the plus x direction. There is an electric field to the left of the sheet. This is just a sheet of charge. There's an electric field to the left. I'm just not showing it. The electric field to the left, it looks the same, right? It's a constant electric field going to the left. Okay, so the magnitude of the electric field is sigma over 2 epsilon 0 in the plus x direction. It's constant. With x, it's just in the plus x direction, but it's a constant. It doesn't vary until you get close to the edges of the sheet. We will stay near the sheet or near the center of the sheet. We won't get close to the edges, or we'll have an infinite sheet so that the field is this. So let's go ahead and calculate the potential energy as you take a test charge. Let's take a test charge, and I'm just going to take a test charge, Q, and say let's move that test charge Q a distance x away from the sheet, and let's look at how the potential energy changes if I move the test charge a distance x from the sheet. So in order to calculate the change in potential energy, let's just say we're going to start from x initial and we're going to finish at x final. So we're moving at delta x, which is x final minus x initial. So let's go ahead and calculate that using our relationship here. First of all, before we get there, let's just make sure we understand the signs. I'm asking for the change in potential energy of the charge Q in a constant electric field E. Is the energy going to go down or up as I move it farther away from the sheet? Think about that. You can stop it and think about it to come to your answer, but the answer is the potential energy should be decreasing as we move farther away from the sheet, because that's the direction a positive test charge would want to move. It wants to move along field lines, and that's decreasing potential energy for a positive test charge decreases along field lines. A negative test charge would decrease opposite field lines. Okay, so let's see if that works out. Let's go ahead and plug in to delta U equals minus F dot ds. What is the force on the top positive test charge? What is the force on the charge? It is the force, it's the electric force, so it's QE. It's the charge of the positive test charge times the field that it's in. That's the force dot ds. ds, and what is ds? ds is the integration variable, but it's the direction that we're moving, and we're moving in the plus x direction. ds is integrating, it's just telling us we're going to integrate over the path length that we're moving, and we're moving in the plus x direction. So that's going to turn into dx. So we're moving in the plus x direction, ds is dx, so let's go ahead and rewrite this on the next page. Let's do a better color than red. Not so angry. Delta U is minus QE dot dx. As opposed to if this was a point charge, we'd be moving in the radial direction, so S would just be R, right? You just got to determine which direction that you're moving in. Okay, and E, so now we can plug in. And what about the dot product? It's going to be minus Q magnitude of E, magnitude of dx, times the cosine of the angle between them. Between what? Between E and dx. E was pointing to the right, x was pointing to the right, so therefore the angle between them, theta, is 0 degrees, and cosine theta is equal to 1. So therefore we got du equals the integral of QE dx. Dot product gone. Okay. What's constant? We can pull out what's constant. Minus Q E is constant because it's a constant electric field, integral of dx. So therefore, delta U is minus Q sigma over 2 epsilon 0 integral of dx. And so we're integrating along the path dx. We're going from x initial to x final. And so the integral of dx is just x evaluated, x final, and x initial. I'm going to write this down and then come back. So I just made sure you understand the notation for an integral. You're integrating over dx. And so the integral of dx is x, and we put the limits in as x final to x initial. And so on the next page we write, therefore, delta U is equal to minus Q sigma over 2 epsilon 0 x final minus x initial, or minus Q sigma over 2 epsilon 0 delta x. So, as x increases, does delta U get bigger or smaller? As x increase, does U increase or decrease? As x increases, right, if delta x equals positive, so as we move away from the sheet, as we move the plus charge away from the sheet along the field line, the delta U is a negative quantity because Q is positive, sigma is positive, 2 epsilon is positive, and delta X is positive. So delta U is negative, and that works, right? The sign is correct. It's always good to check your sign. If this was a minus charge, right? If Q was a minus charge, we would have to plug in a negative Q for the charge in the expression, and that would make the whole thing a positive number. And that means that a minus charge would naturally move towards the sheet, which is absolutely true, right? A minus charge, let's go back to the picture, a minus charge would naturally move towards the sheet, a plus charge would naturally move away. And charges naturally move to where delta U is negative, where the U decreases. Okay. So a couple things to note here. This is delta U. What about delta V? Well, delta V is equal to just delta U over Q. In other words, what if we took the test charge out of the picture? Let's take the test charge out of the picture and just ask, what does the potential of this charge distribution look like? That's just taking the red Q out of the picture. We're dividing it out of the potential energy, and so therefore it is minus sigma over 2 epsilon 0 delta X. It is a constant times a distance with a minus sign, right? The minus sign tells you what direction the potential energy becomes positive or negative in, or how the potential energy, how the electric potential changes. So delta V so let me go to a new picture. So this is the change in potential between any 2 points, x initial and x final, as we get farther from the sheet. That tells us that the change in potential goes down as we get farther away, and that tells you that the change in potential energy for a positive charge goes down as we get farther away. Okay, great. And notice that it is a constant, sigma over 2 epsilon 0 times a distance. So it is the same form as what we started with some arbitrary potential that I started with. But there is a delta here. Let's go ahead and define our zero, right? This is just like a potential energy. We can define our zero. We can say if V equals 0 at x equals 0, we define our zero, therefore V is going to equal minus sigma over 2 epsilon 0 x. So it's minus a constant times x. So if we define our zero somewhere, then we can define what V is rather than what delta V is. No different than a potential energy, right? Potential energy, we always derive a delta U, and then we define where is U equals 0. For a point charge, we say U equals 0 at infinity. For a constant field, we say U equals 0, often wherever x equals 0. So now let's say we have two sheets, right? So we have perhaps a capacitor or just two parallel plates which are oppositely charged with the same charge on either side. And what is the field between these two sheets? We've already seen that before, that the field between the two sheets is just sigma over epsilon 0. We add up, if they've got the same charge density on either sheet, minus and plus, then the sheets add between, and we've got a constant field in between. What happens if we then go ahead and take an electric charge, and we just put an electric charge, a positive electric charge, at some point between the sheets, and we let it go? What's it going to do? From rest, that positive electric charge is going to go from the plus sheet to the minus sheet. What if we have a minus electric charge and we put it somewhere arbitrarily between the sheets? What's it going to do? It's going to go from minus to plus. It's going to move in that direction. Right? So the potential decreases, right? The potential decreases in this direction. This is just repeating what we've said before. And that means that a plus charge will move in the direction of decreasing potential, therefore its potential energy decreases. A minus charge moves the opposite direction of decreasing potential, in which case the minus charge's potential energy still decreases. That's why it's moving opposite the decreasing potential, because of the minus sign. Okay, but what happens if instead I send an electric charge instead of dropping it and from rest in between the two plates? What if I send an electric charge, Q, and I shoot it between the two plates parallel to the plates? So I'm going to take this charge, Q, at the bottom, and just shoot it between the plates so it goes between the plates and comes out the other side. We've talked about this in class before. What's going to happen? If it's a plus charge, it's going to go through the plates and it's going to be deflected by the plates, right? It's going to be moved. In this case, it's a plus charge, so it's going to be moved to the right. So rather than going straight through, it will move to the right, just as if it was a mass in the Earth's gravitational field, right? It's going to be the exact same kind of motion. We've talked about this in class before. Or you've read about it in the book, or you've seen it in a video, but I'm sure we've addressed this before. So if I shoot a charge on a line in the direction of a line parallel to the plates, between the plates, the charge will be deflected by the plates. We've talked about this before. This is a cathode ray tube. It's the way that we It's the way that we can direct charges in any kind of device, whether we're talking about an experiment that we're doing with electricity and magnetism, or in a device where we want to move charges. We can deflect the motion of charges by sending them in through fields of constant magnitude, and then we can easily deflect and figure out how much they deflect by. Though we've done that kind of problem before. That was on the quiz. It was on the test. I'm sorry, I think it was just on the test and on the homework. Let's just think about this from an energy point of view rather than from the kinematics point of view that we've done it before. From an energy point of view, if the charge were to move along the straight line, right, if it wasn't deflected by the plates, along that straight line, let's just call that the x direction, and the deflection direction the y direction, right? So just as if we were in the Earth's gravitational field. Along the x direction, that's an equipotential, right? The potential doesn't change along that direction. So there's no work done on the charge while it's moving along the x direction. Work is not a vector, but there's no work done on it while it's moving in the x direction. So that means that the electric field neither speeds up nor slows down the charge in the x direction, right? So the velocity of the charge in the x direction does not change, just like throwing a ball in the Earth's gravitational field. In the horizontal direction, which we usually call the x direction, the velocity of the ball does not change. But the velocity of the ball does change in the y direction because it's being deflected in the y direction. So it's the charge is being accelerated in the y direction, and so it gains a y velocity. So in the x direction, again, it's moving along an equipotential. There's no work done, no change in energy, and so the velocity in the x direction does not change. But in the y direction, it is accelerated. We can do F equals QE to show it's accelerated, or we can just we can figure out the amount of energy that it gains because it moves through a potential difference as it moves. I think I might have said the wrong thing. I think it says gains potential energy. It does. It loses potential energy. It loses potential energy, gains kinetic energy. Okay, so I've got a joke for you. The king of the jungle, the lion, is having a party. All the animals show up but one. Which one doesn't show up? The giraffe, because he's still in the refrigerator.